Right, good evening, everyone.
Good evening, sir.
Good evening, sir.
How are you?
Good, sir. How are you?
Fine, and you, sir?
Good, thank you. Right, so I hope you have all eaten supper, so we can start our physics lesson. Right, just to make sure, I hope you all can hear me and there's not a lot of interference before we get started.
The screen is half, sir. There's a blue thingy on the screen.
Oh, the screen is off. Okay, just hold
Yes,
on.
there, sir.
Who's this? Okay, please don't
Joshua,
try.
yes, sir, I will play it now.
You're
Yeah.
showing it. Okay, thank you.
Yes, sir.
How is it now?
It's clear, sir.
All right, so it's better now. Right, so I think we'll just give it about 2 or 3 more minutes for the others to join in. There's still others coming through. So I think what we can do for now is we wait for the others to join us. We can look at the question that we were doing previously and finish this question. Right, so we can look at this question. Right, so if you remember this question from the, I think was it yesterday when we were doing the electromagnets. Right, so the electromagnet here, we finished on part 2. That was our last question there. Right, so now they're asking us to calculate the output current is 1.5 amperes. Calculate the power output. They want us to calculate the power output there. How do we calculate the power output based on that there? Let me just keep admitting these people. Right, so please just make sure you have your rough pieces of paper so you can do your calculations. Make sure you also have your calculator. That way we can work through the questions together. Right, so just look at that question. The C part 1. Can we try and work out the power output if our output current is diameter.
Hello.
Hallo, hey.
Joshua, we can hear you.
Ai.
Right. So if there's a lot of background noise, I will mute you from this side. Right. So I'm asking
Sir,
you
the
guys.
blue things are blocking your screen.
Yeah, muting is blocking my screen.
The blue things.
The blue things.
Yes, sir.
I don't see any blue things.
But it's gone now.
Oh, it's gone now.
Yeah.
Okay, let me do this. Full screen. Where is my full screen? How do I put this in full screen mode? Not sure how to do that. Okay, so I hope nothing is blocking the screen. You just let me know as we move on, just to make sure there's nothing interfering with the screen and the audio. Right, so I asked you guys to try and calculate, as we're waiting for the others to join, try and calculate C part 1 and C part 2. Right, we're told that the output current is 1.5 amps. Calculate the power output. If you find your answer, send me your answer in the chat. I'll see your answers in the chat. So just give it about 2-3 more minutes to work through those questions. So please note that it's only 1 mark. Your C part 1 is only 1 mark and the energy is only 1 mark. So if you find the answer, just post it in the chat before we get started with our waves.
Sir,
Yes,
can sir please go up to the question?
to the question.
Yes, please.
All right.
Thank you, sir.
Okay, so have we managed to work out the answers for that C part 1 and C part 2? Please just post your answers before we start looking at the waves. Right. Anyone with the answer for C part one? Anyone with the answer for C part one? For the outputs of the power, what do we get there? Anyone? All right, so the answers are coming through. Right, Rosta is saying the power output is 18 watts. Oh, Chance, your question is asking is, would the coil going around the soft iron core also be considered a solenoid? Yes, it is. It is considered a solenoid, right? So a solenoid, remember, it's just your current carrying wire going around a magnet, right? Okay. Right, so have we all tried to work that out? So please take note, it's just 1 mark. It shouldn't be that difficult. So we already know if we're getting 1.5, let me select my pen. If we're getting 1.5 amps in this part here, 1.5 amps. And we already know the output voltage is 12 volts. So we're using the equation of your P is equals to your VI. Simply multiplying the 12 times the 1.5. If you all do that,
Yes, sir.
Yes,
Yes, sir.
what is my answer?
18 watts.
18 watts, correct. Right. So part two now, it's asking you the energy output in 30 seconds. The energy output in 30 seconds. How do I calculate that? How do I calculate energy being consumed?
Power multiplied by the time.
Yes, exactly. So it's your energy is equals to PT. So our power, as we calculated before, is 18 watts. So we're simply multiplying by how many seconds? 30. Are we following?
Yes, sir.
Yes,
So what
sir.
is my answer? 18 times 30?
540
540 joules.
joules.
That's my answer there. All right, so since we're done with those questions, we can move on to the next part, which is the waves. Right, so with the waves, I think we've covered quite a bit of also questions on that before we broke for the holidays, the Christmas holiday. There's some questions we looked together to do with the calculating your wave speed, the frequency, right? So that's sort of the questions that we want to look at. So I've structured them basically on looking at the basics, the foundations of your waves first, and then we go in deeper, looking at your reflection, your refraction, your refractive index, your diffraction, all of that, right? As well as the sound. When you're looking at the types of waves, you look at the longitudinal waves, how do you calculate the speed of sound, that sort of thing. Right, so those are the questions that we want to look at today. So we'll start off with the multiple choice and then we will look at the structured questions. Right, so question 1, there is asking you sound waves travel at a speed of 1,500 meters per second, right? Through a substance. Their wavelength is 5 centimeters. What is their frequency? What is their frequency? Is it A, 30 kilohertz, B, 75 hertz, C, 7.5 kilohertz, or 300 hertz? Right. Again, you can send your answers in the chat. Right, have we found the answers? Right, so there's a lot of D's. People saying D, D, D. The answer should be A. The answer should be A.
Mm-hmm.
Yeah.
Wavelength is not in
So
centimeters.
Rasta is the one that got that correct. So with
Mhm.
there, you need to look at, you're given a speed, right? So from the speed as well, you're also given the wavelength. So the only equation that you can actually apply is the waveform equation, right? Your V is equals to your frequency times lambda. Are we following? Right. So here, your speed, we can just take it down as 1,500, your V, and then the frequency is what we're looking for, times lambda. This is given as centimeters. So you need to convert this to meters.
Meters.
Are we following to the SI units of? So it's 5 divided by?
100.
Are we following?
Yes,
So
sir.
1,500 is equal to your F times your 1, 2, your 0,05, right? Equals to the 1,500 divided by 0,05, which will give you 30 kilohertz.
35
30 kilohertz, right? Or 30,000 hertz.
hertz, yeah.
30,000 hertz. So that is your 30 kilohertz.
Kilo.
So that's the answer for that one. Are we following? Are we all
Yes,
together?
sir.
Right, let me just admit this, guys. Right, so let's move on to the next question. Question 2. Question 2 says, the speed of a wave is doubled. The frequency remains the same. What happens to the wavelength of that wave? A, it doubles. B, it halves. C, it remains the same. Or D, it becomes 4 times as large. What is my answer? Okay, have we worked out the answer? Or you guys are still working it out? All right. Rasta says A. Okay. And the other guys, what do we think? What do you think? What do we think the answer is? Okay, so the answer is A. Rasta, would you like to explain why you think the answer is A?
Okay, so I just thought about the concept that the speed and the wavelength are directly proportional. And I thought about how you multiply the frequency and the wavelength to get the speed. So if the frequency is staying the same, and if the speed is increasing, then there must be an increase in the
Exactly.
wavelength. Yeah.
Very correct. Excellent. Right. So if you look at that equation that we looked at the top there, your V is equals to frequency times lambda, right? So you remember your lambda is the wavelength. If they're telling you the speed of a wave is doubling, the frequency is staying the same. So it means that your wavelength also has to double. If frequency here is staying the same, right? So what is increasing the speed, right? If this is doubling, frequency is staying the same, the directly proportional means that the wavelength also has to go up by the same magnitude or the same factor. Does that make sense? Do you all get that,
Yes,
guys?
Yes, sir.
All right, excellent. All right, so let's quickly move on to the next question. All right, question 3 shows that what is the name given to the effect that allows the wavefronts to reach point X, shown on the diagram? Is it A, reflection, B, refraction, C, diffraction, or D, dispersion? What is the answer there?
A person can give me a sign of it.
Okay, I see your answers. All right, that's good. Most of you said C. That's the correct answer, right? Your diffraction, right? So remember, diffraction is your interference of your waves with the environment, right? So the only way it can reach point X is when it's interfering with the gaps or the inside of the gaps there. Let me write this part here. So when it goes through the gap, they start to bend like that. I think we've all seen that type of diagram there. Are you following? So that is called diffraction. Right, so the interaction or the interference of your waves with the environment is referred to as diffraction. Right, so let's move on to the next question. So your answer there is C, that's correct. So most of you got that correct. Move on to the question 4. Which 2 points on the wave are exactly one wavelength apart? Which 2 points on the wave are exactly one wavelength apart? Okay, what is our answers for that, for this question? What is the answer?
I think C.
C, huh? Okay, so if you said C, that is the correct answer. C is the correct answer. right? So remember with your wavelength, you're always looking at two successive points. So if you're moving from that point, you now need to look at the point that is successive, that is similar. That is, so if you start at this point, you can see from the wave, it's starting to go down from that point. So you have to look at the point that is going down. This Q to R is wrong because at this point it's going up. So that is not the successive wave point. So you have to go to S. Are we following? Does that make sense?
Yes, sir. Yes, sir.
So another way I can explain it is looking at your troughs. So if you look at the top part of the wave, this point here. So let's say we started at a P. So meaning the next point of the wave, would be at the top there, between R and S. That is one wavelength, right? So if you're looking at that point there, if you go from there to there, that'll be one wavelength. Are we following? So one wavelength is your successive points on the wave. Are we following?
Yes, sir.
That makes sense.
Yes, sir.
Right, so if that makes sense, we can move on to the next part, question number 5. Right, so question number 5 says, the diagrams below show the wavefront diagrams of light as it passes from glass into air. They are magnified many times. Which diagram correctly shows what happens to the wavefronts as they pass through glass A boundary? Is it A, is it B, is it C, or is it D? Right, so I've seen most of you guys' answers. Right, so the answer for this one is D.
Mhm.
The answer, sorry about that. The answer should be D. The answer should be D. Are we following?
Yes, sir.
So if you're moving from the glass to air, remember, if you're moving from a thicker medium, this is the thicker medium, right? To a less thicker medium, right? It's less dense. So you're going to have larger wavelengths. Frequency is it increased or decreased? Or it stays the same? Who can tell me what happens to the frequency?
Okay.
Is it increased, is it decreased, or it stays the same? But the frequency stays the same, guys. So remember, when your wave is moving from this side, the thicker side, the glass side, this part, it's traveling slower, right? Your speed is slower, right? Your wavelength, your V is slower, right? So when it gets out of the glass part where there's less friction or the less dense medium, it travels faster, right? And then you've got a larger wavelength, right? So the frequency stays the same, whether it's in glass or in air. Does that make sense? Using that waveform equation that we explained in the previous question, right? Since we're only changing the wavelength, the speed is decreasing, right? Sorry, it's actually increasing.
Yes, sir.
Yes, sir.
Hi, everyone. Sorry, I lost my internet connection there. Are you all there? Are you still there?
Yes, sir.
Yes, sir.
I'll just reshare my screen. Then we can continue. Okay. Mm. Okay. Just having a few problems with the sharing.
Mhm.
This.
Mr. S, try to restart the iPad. Okay, Maro. Does that.
Okay, Mr. Frank. Yes, Mr. Frank.
All right. All right. Sometimes when it does that, just try to restart the iPad.
Okay.
You know the password, right?
Yes, I do.
Okay. Thank you, sir.
Okay, so I think we can continue for now. Hopefully my internet won't just break off. Right, so with this question, I hope you all understood how we answer that question there. So remember, when you're moving from a thicker medium, to a less thicker medium, your speed of the wave increases because they're experiencing friction in the thicker medium. Yeah, right. So when it becomes into air, it starts to move faster. Are we following?
Yes, sir.
So it starts to move faster there. And then frequency always stays the same, whether if it's in glass or it's in the air or it's in water moving onto the glass, the shallow end or the deep end. The frequency always stays the same. Please remember that. The only thing that's changing is your speed of the wave and the direction of the wave, right? So remember what we're seeing here, this bending here, that is referred to as refraction because of the change in the speed of the wave. Please take note. Right. So if you all understand, we can move on to the next question.
Pardon me, sir. Sir, you said the refraction is what?
The refraction is because of the slowing down of the wave, the change in the speed of the wave.
Oh, okay. Okay. Thank you.
Right. Question 6. Right, let me try and zoom in a bit. I hope you all can see the screen. Right. Question 6 is saying the diagram shows a plane water wave approaching a gap as viewed from above. Right. You've got your wave fronts on this side. And then how could the situation be changed so that the waves on the far side of the gap do not spread out as far, right? You don't want them to spread out too far. How would you change that on that gap thing? A says decrease the speed of the waves, but keep their wavelength the same. B, increase the speed of the waves, but keep their wavelength the same. C, make the gap a little smaller, or D, make the gap a little bigger. So please, this one, it's a bit tricky. So just think about it a bit. They're including concepts of the diffraction, right? So if you know, if you're passing your wave through a gap, it is interfered, it experiences friction through the gap right there, right? Let me just select my pen. right? So it experiences friction here, right? So they're asking you if we want the waves not to travel far, right? So that the waves on the far side of the gap do not spread out as far. What do we have to do? What do we have to do? Right, right. So you guys, your answers are coming through. Please think about it a bit more. They're asking you, they don't want them to spread out as far. The key word there is to spread out as far. We want them not to spread out as far. So what do you have to change about the gap so that they don't spread out as far? Think about it. Right. So I've seen most of your guys' answers. Yes. The guys that said C, that is wrong. Make the gap a little smaller. Remember, when you make the gap smaller, your waves become more circular. So if we decrease the gap and we have it, let's say the size like the, it's now starting the, right? Your waves become circular. So they're spreading out now further. Are we following? Does that make sense?
Yes, sir.
Right, so your answer should be D. You make the gap bigger so that they are more straight. They travel more straight and not circular. They're not spreading out. Does that make sense?
Mhm.
Yes, sir.
So your answer should be D. So the guys that say D, you're correct. Your answer is D. Make the gap a little bigger so that they only travel straight. Right. So please take note of that. Number 7 says a small child throws a stone into a very still pond. Where the stone hits the water, waves travel outwards in a circular pattern until they reach the side of the pond. In a very uncharacteristic move for a small child, he notices that 6 waves arrive in time at 3.2 seconds. Right?
Just hold on.
There's a lot of background noise.
Yes.
Perhaps mute the person. Right. So they were saying in a very uncharacteristic move for a small child, he notices the 6 waves arrive in a time of 3.2 seconds, right? Right. So there, the key feature is that 6 waves arrive at 3.2 seconds. The child has a remarkable accurate internal clock right there, right? So 3 significant figures. What is the frequency of these waves? We're looking for the frequency of these 6 waves. How do we calculate that? So I've highlighted there the key information that you need to take, right? We have 6 waves. This child is noticing 6 waves reaching the other side, right? At 3.2 seconds. And we want to calculate the frequency of the waves. A hint here is remember the definition of frequency. Remember the definition of frequency. Right, so if you said your answer is D, that is correct. Right, so here I'll ask for a volunteer to calculate the answer. How did you get the answer as 1.88? Louise, you're one of the people that got it correct. Would you like to explain to us how you found the answer?
Yes, sir.
Okay.
When sir said remember the definition of or what frequency is, I just took the equation frequency is equal to 1 over the time in seconds.
The time in seconds.
Yes, sir.
Okay.
And then I said 6 divided by 3.2 seconds, and I got 1.875.
1.875.
Yes,
Okay,
sir.
and then you rounded it off to give you the answer as
1.88.
That's great. Excellent. Did we all get that?
Yes, sure.
So that's how you're supposed to calculate it. Are we following? Are we following, guys?
Yes, sir.
So the fact that they said to 3 significant figures, the answer that you get from dividing there, you round it off to 3 significant figures. It should give you 1.88. I hope we're all on the same page.
Yes, sir.
So please remember that. Right, so we move on to the next question. Question 8. So question 8 says, when water travels from deeper water into more shallow water, they are refracted, right? Why does the wave change direction in the manner shown? Why does it change? This one, we've done a similar question and I explained it thoroughly. So all of you should be able to give me the correct answer here. Is it A, B, C, or D? Okay, so from the people that have sent me their answers, only one person got it wrong. Only one person got it wrong here. So the answer that you're supposed to give there, remember, it's going from your deep end, right? It's going from the deep water to the shallow water. So here in the deep water, it's experiencing less friction than in the shallow water. There's more friction in the shallow water. So it will slow down in this shallow water. Are we following? So your answer should be B. Your answer should be B. Are we following? Please, no C or D. Remember, I stated when there's refraction, there is no frequency change. The frequency stays constant. The reason why we have the bending of your waves is because your speed decreases or increases. depending on whether it's passing into deeper water or shallow water. Are we following? So in this case, since it's passing from deep water into shallow water, it's traveling from a less dense medium into a denser medium, right? So it will decrease in speed. Are we following?
Yes, sir.
So your answer should be B for that one. All right, question 9. We have, with skillful use of particular laboratory equipment, water can be used to demonstrate reflection, refraction, and diffraction. For each of these, which row shows whether or not the wavelength of the water waves changes? All right, so I've seen your answers. But I think most of you guys got this correct. Right, so the one that is showing is only refraction. If there is a change or not, the wavelength of the water waves changes. It is refraction. So your answer should be D. Are we following? Your answer is D.
Yes, sir.
This one was also a bit tricky as well. Yes? Is there any question? All right, so that is your answer for that part. Reflection does not show any change. Refraction is the one that shows, and then diffraction does not. Are we following?
Yes, sir.
Yes, sir.
Okay, excellent. All right, so now let's move on to the next part of the questions. I think the next part should be the structured questions. All right, so number 1, as we have there, hold on. Right, so number 1 says figure 6.1 shows a scale drawing of plane wave fronts approaching a gap in a barrier. Right, so you got your direction of your wave travel and the barrier there. A is asking you draw the pattern of the wave fronts after the wave has passed through your gap. Right, so that is 2 marks. So from our diffraction that we're looking at, we know our waves that we get after it's passing through the gap. We just need to look at the distance as well. You can see that the gap there is smaller than the wavelength of your waves. Can you notice that? This is the wavelength.
Yes, sir.
And the gap size is smaller. So it means you're going to get circular waves coming from there. Are we following?
Yes.
So they have to be more circular.
Bending of the waves.
Like that. Are we following?
Yes, sir.
All
Now say if they were closer together.
If they were closer together, which part? Which part are you asking?
The traveling of the wave. The waves.
Yes, the traveling of the wave.
Were closer together.
Oh, okay. So if you're saying the wavelength is smaller, you've got like
Yes.
waves here. They'll be more circular. They will be
Still
more
also.
circular. Yes. The only thing that changes is the gap size, right? So let me just erase this. Right. So let's say for now, we've increased the gap size, right? We have it starting there. Right, so the gap size now has been increased to more than the wavelength here. These will be now a bit more straight, like this. Does it make sense?
Yeah.
So try and see that when it's small like this, there's more interference from the edge of your gap. When it's bigger like that, there's less interference of the wave. So that's why it becomes more straight like this. Can you see that?
Yes, sir.
I hope that makes sense. All right, so if you do that, you get your 2 marks. All right, so we'll move on to part B. So it's now asking you the wave producing the barrier has a wavelength of 2.5 centimeters and a speed of 20 centimeters per second. Calculate the frequency of the wave. Calculate the frequency of the wave. Can we all try and do this question together? What do we get? Are we done? Right, so let's do it all together. So here we have the wavelength as your 2.5 centimeters. So immediately, please convert these into your SI units. We've got the speed as well as 20 centimeters per second. We also need to convert this. So when I convert 2.5 centimeters into meters, what do I get?
Zero point zero 0.025
meters.
0.025 meters.
5 meters, right? You're just dividing by 100, guys. So now with the speed, it should be in meters per second. It should be in meters per second. I just want to convert everything into SI units. What do I get? How do I convert my 20 centimeters per second into meters per second? 0.2. So you just divide it by 100 again, guys. Since it's centimeters per second, we just need to convert the centimeters into meters part. So you just divide by 100 again. So you get your 0.2 meters per second. So we now have our wavelength in meters, we have our speed in meters per second. We now apply the waveform equation of frequency times lambda. So your frequency would be equals to what? My frequency is what?
8, right? Or like 0.2 divided by 0.25.
So
Give
you
8.
simply divide the speed by the wavelength, which is my 0.2 divided by 0.025, which gives me, what is the answer?
8.
8.
8 hertz, right? Or you can say 8 waves per second, right? But then this is usually the agreed one, the 8 hertz. Are we following, guys?
Yes, sir.
Yes, sir.
Right, so that is my answer for that part. I hope you are all following. Now it says state what happens if anything to the frequency of the wave as it passes through the gap. What happens to the frequency?
It stays the same.
It stays the same. The frequency stays constant. The frequency stays constant. Are we following?
Yes, sir.
Right. So that is my answer there. Right. So Maria is asking a question in the chat. She's saying, so is it really necessary to convert the units? Because even if you do it using centimeters, it gives the same answer. Oh,
Gives
really?
the same answer, yeah. Yeah, it does.
Okay. Or because both of them are in centimeters.
Yes, sir.
So it
Yeah.
cancels out. Yeah, it makes sense. But then personally, I'll just advise, make sure you convert them to SI units. Always
sir.
convert them to SI units, because sometimes they might be marking you on that as well. Like this person, do they use centimeters or meters? So you never know. Try to always use SI units when you're doing your calculations. Right. Let's move on to the next part. So this one is saying, explain in terms of diffraction why a car radio may pick up low frequency radio signals, but not pick up high frequency radio signals when the car is traveling behind a hill. So this one, it's tricky. You have to think about it. Look at the properties of your waves and when they're passing through a barrier, what happens? Right, so it's behind the hill. Your car is behind the barrier, right? So here I'm just giving you hints. What is happening? This is diffraction, right? They're asking you to explain what is happening. Why is it picking up low frequency radio signals, but they're not the high frequency radio signals? Anything, guys? Do we know why it's picking up the low frequency and not the high frequency? So I'll just try to explain it like this. Your gap, and then your wave, right? So let's say that is my This is my low frequency. Low frequency. Can you all see that?
Yes, sir.
Mhm. And then I have my gap, same type of gap, but then my high frequency. What is happening there? Who can explain to me? So that should be a bit of a hint so that you guys can think about it as well. What is happening? Anyone would like to try?
Sir, is it because for the low frequency they'll be spread out more if they
Exactly.
go through the gap, like in comparison to
Uh-huh. So remember,
high frequency?
if your wavelength there, if the gap is smaller, right? These ones would be more spread out because the wavelength is bigger than the gap. Are we following? So they'll be more circular, therefore will spread out more than the wavelength that is what? That is smaller. There's interference there. Who's listening to music? Ndala.
I'll mute you, Mike.
Right. Does that make sense, people? So the size of the gap is not changing. So your low frequency waves or your radio signals, the low frequency radio waves
A longer wavelength.
have a longer wavelength. Sorry about the bad handwriting. Very hard to write on an iPad here. Right, so it's got a longer wavelength. Therefore, will spread out more. Than the high frequency radio waves. Are we following?
Yes, sir.
Does that make sense?
Yes, sir.
Right. So that is answer. We move on to the next part. So these questions, I think we've covered a lot about the wavefronts traveling from a deeper end to a shallow end, right? So I think you guys should be able to answer these questions by yourself. Do you think you guys can do that now? Especially with this diagram. Are you now confident with these questions? That was a quick no.
Wait, yes, sir.
You're saying yes, you'll be able to answer it. It's all about confidence. If you're not confident enough, we can go over it together. Right? But then we probably won't be able to finish all the questions today. Right? So if you guys still feel like you're a bit sketchy about answering this type of diagrams, yes?
Are we gonna get these papers tomorrow?
Yes.
Okay.
I think we can share these questions, especially the hard copies tomorrow as well.
Yes, sir, not soft copy.
Yeah. Yeah, I'm also my eyes are really hurting from looking at the screen. Right. So should we skip this question or you guys want to look at it? Skip. What was that? Was that Sven?
Interesting.
Right. So let's look at a different question. Right. Let's see. I want to look for a particular one that might be interesting. Here it's asking, state what happens to the frequency of the water. We already looked at that. Shows a metal strip held in a clamp. The end of the strip is pulled down and released so that the strip vibrates. X and Z are extreme positions of the end of the strip during this vibration. Y is the mid position. Explain what is meant by frequency of vibration of the strip. Right. So this one's it's actually to do with your definitions. So you should know your definitions, right? So I think this one we can also skip. Right. So yeah, with frequency, you're just looking at the number of times it's moving up and down. It's going from your X to Z in a second. Are you following? And then the amplitude, you're looking at how much displacement, how far is the X point, the position of X from your Y. Are we following? So please note the difference there. Right, let's see. Echoes. Right, so here it's saying figure 5.2 shows two tall buildings A and B that are 99 meters apart. A student stands at P so that his distance from building A is 33 meters. After clapping his hands, once he hears several echoes, the speed of sound in A is 300 meters per second, right? It's 330 meters per second. Calculate the time interval between clapping his hands and hearing the first echo. Right. Well, how do we do that thing? So please take note here. The buildings are 99 meters apart, right? I'll just quickly highlight that for you. Right? 99 meters apart. The closest standing building A, that's the closest building B. That's 33 meters. Right? So obviously building B will be further. So they want you to calculate the first echo. How do we do that? Anyone would like to try? How do we calculate the first echo?
Okay, so I assume
Yes.
that the first echo would be because of the closest building, which is A. So then I
Yes.
simply took the speed of sound in air, which is 330 meters per second, and I divided it by the distance, which is 33 meters, to get the time, which I got 10 seconds.
That's correct, right? So we already given the distance between P and the building, right? The P is the person A, right? So if it's 33 meters, we're looking for the time taken. So the time will just be your distance divided by the speed. Are we following? Right, so you've got your 33 meters divided by 330 meters per second, which gives you an answer of, is it 33? No, it shouldn't be 33.
And so,
what's the distance that I'm using? Remember, this is an echo.
Oh.
So what distance am I using?
Is it the entire 99?
Is it 99?
No, I'm asking,
No.
so isn't it just 33?
No. From clapping. They're saying after clapping his hands, once he hears several echoes, right? Calculate the time interval between clapping his hands and hearing. So remember, when he claps his hands, the sound is starting from P. Starting from P. So it travels to the building A and is reflected back to him. So it's traveling that distance twice.
66.
Oh,
It's traveling that distance twice. So you say you're 33 times 2. This is an echo. So it travels the distance twice. Are we following?
Yes, sir.
So it will be your 66 divided by 330.
0.2.
0.2.
Is 0.2 seconds. So it takes 0.2 seconds for this wave to the first echo. Right? Did you all get that? Yo, you guys have a lot of dogs, huh? Right. Part 2. It's asking for the time taken for the third echo. How do we calculate that? The third echo. I'll go back to the diagram so that you guys can have a clear picture on what is happening. So remember, when he clapped his hands, that sound travels in all directions, not just to building A, also to building B, right? Are we following?
Yes, sir.
So let me just change my color here, just to show you the other way, right? So the other one will travel from P all the way to building B and then travel back to P, right? Are we following?
Yes, sir.
That is the second echo, but then they're asking for the third. Where does the third come from? Where does the third echo come from? Where does the third echo come from? So remember, this still on the same diagram. I'll go back to my blue. You still remember the sound which went to building A and then back to P. That will also continue all the way to building B and then reflect again coming back. Are we following? That is your third echo.
Oh.
You get me, guys? That is your third echo, right? Since your distance between P and building B is greater, it will take longer for the second echo to come back. So your first echo will register as the third echo because it's traveling less distance, right? So let me just change my color here. Right, so from when you subtract your 33 from 99, you get what? You get 66, right? 66 meters, right? So your first echo, the second echo, is traveling 66 times 2, right? So that is way more than the first echo, right? So when the first echo travels this distance A, it will be already going back to building B before building B gets to P. So when building B, your second echo reaches P, this one will be traveling all the way this way or coming back. Does that make sense?
Yes,
I
sir.
hope you can all understand that jargon there. Right. So my third echo is the wave from the start, the first echo that we're dealing with. That's the third echo. So since they're asking us for the time from clapping of his hands to hearing that echo, we start again. It's 33 plus 33, which is 66. And then 66 times 2, what is that? What is 66 times 2?
132.
Come again?
132.
132 meters, right? So you add your 66 plus 132 meters. So we're adding the 132 plus 66 meters. What do we get?
198.
188 meters.
98.
So that first, for that third echo, the sound is traveling 188 meters. That's the distance it's traveling. So the time it will take will be 188 divided by 330.
So
What is the answer?
198.
198.
198 seconds, right?
Mr. Sir.
No, sir.
No, the distance is 198.
Oh, okay,
Not
thank you.
188.
Okay, thank you. I was a bit lost there. So it's 198. And what is my answer? The time taken?
0.6.
0.6 seconds. Does that make sense?
Yes, sir.
So that's how you're supposed to calculate that. I think our time has run out. All right, so I think with the rest of the questions, we'll look at them tomorrow as well. So we'll try and print these questions for you so that you can also look at them. So that when we do the lesson as well, it'll be also faster. You don't have to be waiting for you guys to work them out. You already have your answers, right?
Yes, sir.
Right. So these are the rest of the questions that you guys might look at by yourself, and then we'll cover them tomorrow as revision. Right. So I hope you guys, this was helpful and you guys saw how to tackle those questions with waves. Some can be very tricky, so please take your time to analyze the question before you answer.
Yes, sir.
So if you guys have no questions, I think we can call it a day. Enjoy the rest of your night, or good night if you're sleeping. But I think most of you be up since you're studying for maths. Right.